I would like to introduce our first speaker is Professor Sarah Yumi Lee. And Sarah obtained his bachelor degree from KAIST in 2009 and her PhD in organic chemistry from MIT with Professor Greg Fu in 2014. Then she joined the group of Professor John Hardwick at UC Berkeley as an NIH postdoc fellow. In March 2018, she started her independent career in the Department of Chemistry at Yonsei University as an assistant professor. Her research interests include the development of a catalytic platform for stereo-selective chemical synthesis. She's one of the current Science of Synthesis earlier career advisory board member. She also received the TMA Chemistry Journal Awards in 2022. And today, the title of her talk is Still Divergent to Catalytic Conjugate Additions. Sarah, we're ready for your talk.
Okay. Can everyone hear me?
Yes, very well.
And my screen's showing well as well.
Yes. Yes.
Okay. So okay. Is it still everything look good?
Everything looks good. You can just go ahead.
Okay. Thank you so much. Thank you, Professor Liu, for a kind introduction. And I also do appreciate this opportunity to be part of the web seminar, Rising Stars in Organic Synthesis, with other amazing speakers today. So my research group has been interested in developing new catalytic platforms for stereoselective chemical synthesis. And for today's talk, I'd like to share one of my research program on stereoselective conjugate addition reactions. So we are particularly interested in the conjugate addition of carbon nucleophiles to electron-deficient alkenes to create the stereogenic carbon-carbon bond. And this product can serve as versatile building blocks in organic synthesis. And especially, we've been interested in developing stereodivergent catalysis. And given the audience, probably all of you are familiar okay, so it's not okay. So all of you are familiar with the concept stereodivergence. And let's look at this compound with two stereogenic centers as an example. So since this guy has two stereogenic centers, all four stereoisomers are possible with two anti-diastereomers and two syn diastereomers. In stereodivergent reactions, all of these four stereoisomers are selectively accessible during the reaction. And you can imagine achieving stereodivergence can be challenging because sometimes you have to overcome the large mismatched interactions at the bond forming event. And there have been a lot of strategies investigated, including sometimes people leveraging the catalyst control along with the altering the alkene easy geometry, or sometimes people use sequential reactions to ensure the control of stereochemistry as well. And one conceivable approach is to do dual catalysis, where you use two chiral catalysts. And in these reactions, when you generate the product with two stereogenic centers and two chiral catalysts control each stereogenic center independently, then based on the catalyst combinations, you can access all four stereoisomers selectively. And this concept has been first realized by Professor Eric Correa in 2013. And in this reaction, he generated iridium allyl electrophile from the reaction with the iridium catalyst and allylic alcohol. And he generated this enamine nucleophile, which is the chiral nucleophile, from the chiramine and this aldehyde nucleophile. And these two chiral intermediates react together to create this carbon-carbon bond. And based on the catalyst combinations, all four stereoisomers have been selectively accessible. And upon this really a nice report, a lot of people investigated these stereodivergent dual catalytic reactions. And especially, a lot of reactions have been investigated with the use of this transition metal-based allyl electrophiles. And this can be coupled with this catalytic chiral nucleophilic intermediates to generate a lot of allylated scaffolds. And while all these reactions are really amazing, and I love these reactions, but the accessible product could be all allylated scaffolds. And allylated scaffolds are really useful scaffolds. However, we thought if we can achieve this stereodivergence in other types of organic reactions, such as conjugate addition reactions, and we thought that would be an important advance in this field. And one of the common strategies to do asymmetric reaction is to generate this chiral iminium electrophile. And this can be generated by the condensation between alpha beta unsaturated aldehyde and chiral amine catalyst. And especially this chiropyrrolidine, Jorgensen Hayashi type catalyst had proved to be the effective catalyst for the conjugate addition of these aryl acetic acid derivatives. And you can imagine the acidity of this alpha position can be really important because after all, you have to deprotonate this guy to generate and enolate nucleophiles. And therefore, the scope of these reactions includes thioester, ketone, and all these have highly acidic benzylic protons. And when it comes to ester nucleophiles, the beta aryl group has to include this nitro, ester, or nitrile highly electron withdrawing group to ensure the acidity of this benzylic protons. So you can see here there is a reactivity limitation. And moreover, since this chiral iminium electrophile controls the stereoselectivity, only this chiral center has been controlled, and this center is not controlled, and therefore the observed diastereoselectivity is often just a 1-to-1 or up to 3-to-1. So there is a selectivity issue in this reaction. So we thought about developing stereodivergent conjugate additions. Then we might be able to overcome both the reactivity and selectivity challenges in this reaction. And especially, we've been interested in generating this iminium electrophiles. And we thought about generating this chiral enolate through the reaction of aryl acetic ester and the Lewis base. And since this ester will be activated by the base, we might be able to overcome the reactivity issue. And since two chiral intermediates would be reacting, and we might be able to generate all 4 stereoisomers selectively in this reaction. And in the reaction mechanism, we thought maybe the Lewis base, such as isothiourea BTM, reacts with this aryl acetic ester, which is perfluorophenyl ester especially. It undergoes acyl substitution, and now it has this acidic alpha proton and is deprotonated by this phenoxide and generate this enolate intermediate. And the perfluorophenol generated in this step now in turn participating in generating this iminium electrophile. And these 2 chiral intermediates react to form a carbon-carbon bond, and water goes back in, and then perfluorophenoxide rebound to regenerate both of the catalysts and also creating this conjugate addition products with 2 stereogenic centers. And after considerable efforts, okay. All right. Next slide. Excuse me. Okay, there you go. After considerable efforts, we were able to identify the reaction conditions of conjugate addition of this ester nucleophile to this cinnamaldehyde, and did generate the diastereomer in 83% yield with 99% EE as a single diastereomer. We used this pyrrolidine with 2 CF3 groups and this BTM isothiourea catalyst. And we are showing this anti-selective reaction. And in the absence of either of the catalysts, there was essentially no conjugate addition reactivity, so both of the catalysts are required for this reaction. And the absolute configuration can be explained by the transition state where these two stereodirecting groups are positioned far apart, and there is a stabilizing pi cation interactions in the transition state, and that creates this SR anti-diastereomer. And we are currently investigating this transition state through DFT calculations as well. And under this anti-selective reaction, a lot of the esters with various aryl groups can be employed, such as just the phenyl, or a lot of substituted phenyl, even including electron donating groups, and also this pi conjugate system or thionyl groups. And in most cases, all the products were obtained as a single diastereomer with 99% EE. And the beta substituents on the electrophile can be various aromatic groups as well. And we have only one example of a methyl substituted alpha beta unsaturated aldehyde. And while it's only 33% yield, but we were able to achieve 99% EE with 7-to-1 DR. And so far, I've been showing you the anti-selective reaction. And for this reaction, we use either R-R combination or S-S combinations. But I told you earlier that we wanted to develop the stereodivergent reaction, so we gotta be able to generate syn diastereomer. And fortunately, when we used R-S catalyst combinations, we were able to create the syn diastereomer with OK selectivity of 99% EE, 8-to-1 DR, but only in 20% yield. And this is likely because of the mismatched interaction at the bond forming event. And we thought maybe our catalysts are too big. So especially it has two CF3 groups, it might be too big. So we thought about using a little bit smaller catalyst with the phenyl group, and it improved the yield up to 40%. And after this, we also tried a lot of different variations. So we ended up finding the reaction conditions with 20% catalyst loading for each. And we also have to use water as a co-solvent. And we don't know the effect clearly at the moment, but we are actually investigating with DFT calculations on this. But under these conditions, we were able to create the product in 85% yield with 12-to-1 DR. Unlike anti-diastereomer, the syn diastereomer was not stable on the column chromatography. So we isolated the product after a hydrolysis of this perfluorophanyl ester to this acid product. So we isolated 1,5-aldehyde acids. So various syn diastereomers of this aldehyde acids were isolated under our conditions as well. So starting from these simple starting materials, just the ester and alpha beta unsaturated aldehyde with RR or SS catalyst combinations, we were able to create anti-diastereomers. And with RS combinations of the catalysts, we were able to create syn diastereomers of the conjugate addition products. So all four stereoisomers are selectively accessible. And we also thought our products, 1,5-aldehyde ester, are versatile building blocks in organic synthesis. And through chemoselective reactions, it can be derivatized to different carbon compounds. But we were more interested in this alpha position of the aldehyde, because with the right amine catalyst, we can create this chiral enamine intermediate. And with the choice of suitable electrophile, we might be able to create this third stereogenic center. Then we can create the compound with 3 contiguous stereogenic centers in an acyclic system. And indeed, when we tried the reaction with the proline catalyst and NCS as our electrophilic chlorine source, we were able to create this third chlorine stereogenic center with 14:1 DR, which is good. But unfortunately, regardless of the choice of L or D proline, we obtained exactly the same diastereomer, indicating this is just the substrate-controlled diaster selectivity rather than catalyst-controlled selectivity. And we were able to also generate this fluorine-chlorine center through the sequential fluorination and chlorination reaction. But again, this was the only substrate-controlled diaster selectivity. But if you think about the reaction where, like using our synergistic catalysis, we can create all 4 stereoisomers. And if it can undergo the catalyst-controlled enamine catalysis, then you can create all 8 stereoisomers of the compound containing 3 stereogenic centers selectively. And we were able to achieve that through asymmetric fluorination reaction. So we used this carbaperoline as our amine catalyst, and we used NFSI, which is the electrophilic fluorinating reagent, as our fluorine source. And regardless of this anti-diastereomer or syn diastereomer, with the use of this S amine catalyst, we can create this S center. And with our catalyst, we can create this R stereogenic center. And if we use different enantiomers of the conjugate addition product, we can access the rest of the 4 other stereoisomers of the product. So just to summarize this work, we are the first group to use iminium electrophile in stereodivergent Dewar catalysis. And I hope I convinced you that this reaction can create really useful chiral building blocks in this chiral building blocks for organic synthesis. And in continuing our interest in stereodivergent Dewar catalysis with iminium electrophiles, now we are combining this iminium catalytic cycle with the Lewis acid catalysis. So previously we used a Lewis base catalysis with iminium catalysis.
Sarah,
yes?
Sorry for interrupting. It's time is up, so probably we can just wrap up a little bit quickly.
Okay, so I'm almost done actually. So we are developing new reaction, and also we are trying reaction other than a conjugate addition, also the Saldo reaction. So I showed one program on stereodivergent catalysis, and we are also developing new molecular catalyst these days as well. And all of this work is done by my students. So I thank my students. And again, thank you, Professor Shiryu, for this, and teammate for this opportunity. And thank you all for kind attention.
All right, thank you, Sarah, for such a wonderful talk. And it's a really beautiful results by using this stereodivergent of Dewar catalysis by using 2 catalytic systems. It's a pity we don't have a discussion today. So thank you very much, Sarah, for a wonderful talk. We'll just move on to the second speaker.